Hey, what's up, Cybercreed family? You know what's absolutely mind blowing? Right now, as I'm recording this video, YouTube is processing over 500 hours of video content every single minute. That's like having 500 people upload hour long videos simultaneously, non stop 24/7. And here's the kicker, they're not just storing these videos, they're transforming each one into multiple formats, distributing them across the globe, and serving them to over 2 billion users with the kind of speed that makes you forget you're literally streaming data from servers thousands of miles away. But here's what's wild, most people think YouTube is just a website where you upload videos and they magically appear. Oh no, my friend. What we're looking at here is one of the most sophisticated distributed systems ever built, and today we're going to tear it apart piece by piece to see how this engineering marvel actually works. So buckle up, because we're about to dive deep into YouTube's video processing pipeline, and trust me, by the end of this video, you'll never look at that little play button the same way again. Let me start with some numbers that'll put this whole thing in perspective. YouTube handles over 117 billion monthly visits. That's not views, that's visits. To put that in context, that's like every single person on earth visiting YouTube 15 times a month. And honestly, that's probably not far from the truth. But here's where it gets really interesting. YouTube isn't just serving cat videos from a single server in someone's basement. They're running on the same infrastructure that Google built over the last decade. We're talking about a content delivery network that spans over 200 countries and more than 1,300 cities around the globe. Now, you might be thinking, okay, that's impressive, but how hard can it be to serve some video files? And that's exactly the kind of thinking that'll get you in trouble when you're trying to build something at this scale. Because YouTube isn't just serving video files, they're performing real time magic tricks that would make Houdini jealous. So let's start at the beginning. You've just recorded the most epic video of your cat doing something ridiculous, and you hit that upload button. What happens next is like watching a perfectly choreographed dance between dozens of different systems. First, your video gets ingested through something called RTMP, Real-Time Messaging Protocol. Now, if you're doing live streaming, they also use WebRTC for browser-based applications, but for regular uploads, RTMP is the workhorse. Think of RTMP as the bouncer at a really exclusive club. It's making sure your video meets all the requirements before it gets let into the party. But here's where things get absolutely insane. The moment your video hits YouTube's servers, it doesn't just sit there waiting. Oh no. It immediately gets thrown into what I like to call the transcoding tornado. Now, transcoding is basically the art of taking your single video file and turning it into multiple different versions. And when I say multiple, I mean YouTube creates versions of your video in 144p, 240p, 360p, 480p, 720p, 1080p, and 4K. That's 7 different versions of the same video, each optimized for different devices and internet speeds. But wait, it gets better. They're not just changing the resolution, they're also using different codecs for different scenarios. And this is where YouTube's strategy gets really clever. For videos that might only get a few hundred views, YouTube uses good old H.264. It's reliable, it's fast to encode, and frankly, it gets the job done. But here's where the magic happens. Once your video starts getting more popular, YouTube automatically re-encodes it using more advanced codecs. When your video hits around 3,000 to 5,000 views, YouTube switches to VP9. Now, VP9 is Google's open source codec, and it's brilliant because it can compress videos with HD and 4K quality at literally half the bandwidth of other codecs. That means faster loading times and less data usage for viewers. But if your video really takes off, I'm talking about millions of views, YouTube brings out the big guns, AV1. This codec is so efficient it can deliver the same quality as VP9, but with 30% less bandwidth. The only catch? It takes about 18 times longer to encode than H.264. But when you're serving millions of views, that computational cost becomes worth it. And here's something that'll blow your mind. YouTube actually re-encodes viral videos. When a video goes viral, it gets subjected to another round of compression to ensure the same visual quality at an even smaller file size. It's like YouTube saying, oh, this video is popular, let me make it even more efficient. Now here's where YouTube's engineering gets really sneaky. They don't just serve you one big video file. Instead, they chop every video into tiny segments, usually between 2 to 6 seconds long. Why would they do this? Well, imagine you're watching a 10-minute video. and your internet connection suddenly gets worse. With traditional streaming, you'd have to wait for the entire video to buffer at a lower quality. But with segmentation, YouTube can switch quality levels every few seconds based on your current network conditions. This is called adaptive bitrate streaming, and it's powered by protocols like HLS, HTTP live streaming, and Dash, dynamic adaptive streaming over HTTP. These protocols are constantly monitoring your connection and making real time decisions about which quality segment to serve you next. But here's the part that nobody talks about. YouTube uses machine learning algorithms to predict what quality you can handle. They're analyzing your past bandwidth data, your current network conditions, and even the playback statistics from your device to determine if they can push higher resolution content to you. It's like having a personal video quality butler that's constantly optimizing your experience. Now, storing and processing all these video segments is one thing, but getting them to users around the world is a completely different challenge. And this is where YouTube's CDN architecture becomes absolutely crucial. YouTube leverages Google's content delivery network, which is built on the same infrastructure that serves YouTube itself. They've got edge locations in over 1,300 cities worldwide, which means when you click play on a video, you're probably getting it from a server that's relatively close to you geographically. But here's where it gets really technical. YouTube uses something called QUIC, Quick UDP Internet Connections. This is a protocol that Google developed specifically to reduce the number of round trips needed to establish a connection. Traditional protocols require multiple back and forth communications before they can start sending data. QUIC cuts through that like a hot knife through butter. And speaking of cutting through things, let's talk about load balancing. YouTube uses something called maglev, which is Google's load balancer. Maglev provides consistent hashing and session persistence, which means if one server fails, your video stream doesn't skip a beat, it just gets rerouted to another server instantly. Now, let's talk about where all these videos actually live. YouTube uses a multi-tiered storage system that's honestly more organized than my sock drawer will ever be. They've got what they call hot storage for frequently accessed content. Think trending videos, recent uploads, and live streams. This stuff is stored on high-performance systems that can serve content instantly. Then there's warm storage for videos that get accessed regularly but not constantly. And finally, there's cold storage for archived content that rarely gets viewed. It's like having a filing system where the most important documents are on your desk, moderately important ones are in your filing cabinet, and old stuff is in the basement storage. But here's what's really impressive. This entire system is managed by Google's Bigtable and Spanner databases. Bigtable handles all the user interaction data like comments, likes, and recommendations. It's chosen specifically for its low latency, high throughput capabilities. Meanwhile, Spanner manages transactional data like user watch history and session tracking, providing consistency across YouTube's global user base. Now, let's talk about the hardware that's actually doing all this processing. YouTube's servers aren't just regular computers. They're equipped with specialized encoding chips, custom GPUs, and Google's own TPUs, tensor processing units, that are specifically designed to accelerate video processing and machine learning workloads. And here's something that's really cool. YouTube uses FFmpeg, which is an open source software suite for handling multimedia data. So even though they're running on custom hardware worth millions of dollars, they're still using open source tools that you could theoretically run on your laptop. The difference is scale and optimization, but processing and serving videos is only half the battle. The other half is figuring out what videos to show to whom. YouTube's recommendation engine is powered by TensorFlow and uses graph structures to map relationships between users and content. This system is analyzing your watch history, your likes, your search behavior, your demographics, and probably things you don't even realize you're sharing. It's using collaborative filtering, deep learning, and matrix factorization techniques to predict what you want to watch next. And here's what's wild. This recommendation system is running in real time. Every time you interact with a video, that data is immediately fed back into the system to refine future recommendations. It's like having a personal curator who's constantly learning your preferences and getting better at predicting what you'll enjoy. Now, let's talk about what happens when things go wrong, because at this scale, things go wrong constantly. YouTube employs something called graceful degradation. During high traffic or load spikes, instead of everything crashing, YouTube reduces the load on non essential features while keeping video playback running smoothly. They also use predictive scaling, where AI models analyze historical data to predict when servers might experience overload. This allows YouTube to scale preemptively, spinning up additional resources before problems actually impact users. And this is all managed by Kubernetes for auto scaling microservices and Google's internal cluster manager called Borg for deploying and managing large scale services. It's like having an army of robots constantly monitoring and adjusting the system to maintain optimal performance. Now, if you're wondering what this whole system is built with, YouTube is primarily written in Java, Python, and C++. Python is used for scripting tasks, back-end development, and deployment. For the front end, they use a lightweight JavaScript framework called Structured Page Fragments, SPF, that enables efficient navigation and seamless page updates. And honestly, this is one of the things I love about YouTube's architecture. They're not using some exotic proprietary technology. They're using languages and frameworks that most developers are familiar with, but they're using them at a scale that most of us can't even comprehend. So, why does all this technical complexity matter? Well, according to YouTube's 2024 impact report, their platform contributed $55 billion to the US economy alone. That's not just from advertising revenue, that's from the entire creator economy that exists because YouTube can reliably deliver content to billions of users. But here's what's really impressive: all of this infrastructure scales automatically. When a video goes viral and suddenly gets millions of views, YouTube doesn't need human intervention to handle the load. The system automatically allocates more resources, re encodes the video with more efficient codecs, and distributes it to more edge locations. So, what can we learn from YouTube's architecture that we can apply to our own projects? First, design for scale from the beginning. YouTube didn't build their current system overnight. They've been iterating and improving it for over a decade. But the principles they use, like segmentation, adaptive streaming, and multi tiered storage, can be applied to smaller projects. Second, invest in monitoring and predictive scaling. YouTube's ability to handle traffic spikes isn't magic, it's the result of sophisticated monitoring systems that can predict and respond to changes in demand. Third, don't be afraid to use open source tools at scale. YouTube proves that you don't need proprietary technology to build world class systems. What you need is good engineering practices and the right architecture. And finally, always think about the user experience. Every technical decision YouTube makes, from codec selection to CDN placement, is ultimately about delivering the best possible experience to their users. Looking ahead, YouTube is continuing to push the boundaries of what's possible with video processing. They're investing heavily in AV1 adoption, exploring new compression techniques, and constantly optimizing their infrastructure for better performance and lower costs. And honestly, that's what makes this stuff so exciting. We're not just looking at a static system, we're looking at a constantly evolving platform that's pushing the entire industry forward. So there you have it, CyberCreed family, the complete breakdown of YouTube's video processing pipeline. From the moment you hit upload to the moment someone watches your video on the other side of the world, there are dozens of sophisticated systems working together to make it all happen seamlessly. What I find most impressive about YouTube's architecture isn't just the scale, it's the elegance. They've taken an incredibly complex problem and broken it down into manageable pieces that work together beautifully. It's like watching a Swiss watch, but instead of telling time, it's delivering cat videos to billions of people. If you found this deep dive as fascinating as I did, make sure to hit that subscribe button and let me know in the comments what other tech systems you'd like me to break down. And if you're working on video processing or streaming projects yourself, I'd love to hear about the challenges you're facing. Thanks for watching, CyberCreed family, and I'll see you in the next one.